Okay, in part 2 of lesson 5.5 on recursive rules for arithmetic and geometric sequences, we're going to look at a couple of special sequences and then do a word problem here. So 1, 1, 2, 3, 5, if you remember, is the most famous sequence of all, the Fibonacci sequence. Back at the beginning of the unit, we talked about this sequence, and I mentioned to write this in explicit form is really hard to do. There is one, but again, it's really difficult. And understanding the way that this works, to get 2, I take 1 plus 1 and I get 2. And then to get the next one, I take 1 plus 2 and get 3, 2 plus 3 and get 5, 3 plus 5 and get 8, 5 plus 8 and get 13, and so on and so forth. So I'm always adding the two previous terms together. And I said way back when we first talked about this that a recursive rule would do the trick, and we would learn about that at some point. Well, guess what? Now's that point. So if I'm going to write this recursive rule, I know that to get the nth term, I take the two previous terms and add them together. So the two previous terms added together would look something like this. I'd have a sub n minus 1, which is the previous term, plus a sub n minus 2, which is the term that came 2 before it. So this would be the two previous terms that I'm working with. Now, with our recursive rules, just like the two we did up here, we always have to say where we started, so I have to identify what's the first term. Now, with this one, because I'm using two previous terms, I actually have to identify not just the first term, but also the second term, because I have to know, I have to have two terms to get rolling with this. So the first term is 1, and the second term is also going to be 1. And if I know those two terms, then I can go ahead and find the third term, the fourth term, the fifth term, the sixth term, etc. Okay? So there would be the Fibonacci sequence written as a rule, recursive rule at that. Now this one on the right, this is kind of a tricky one that maybe you could do this explicitly, but there's a math thing that we haven't learned yet. We will get there, but for right now, I notice that as I go from term to term here, let's see, imagine this is 1 over 1, just for fun here. 1 to 1, 1, 1, 1, 1, 1, it's all ones in the top. Okay, so as I write this rule, boy, I'm going to be leaving a 1 up here. Okay, now as I go from 1 to 2 to 6 to 24 to 120, I'm adding 1, I'm adding 4, I'm adding a bunch. Maybe I'm multiplying, it's 1 times 2 is 2. Okay, well, how do I get from 2 to 6? Think about multiplying. Well, that'd be 2 times 3 to get 6. Okay, so this is here would be times 2. And then from here to here would be times 3. And then from here to here would be times 4. Ooh, and 24 times 5 is 120. So I'm multiplying by, now, think about this. This is the first term, this is the second term, this is the third term, this is the fourth term, this is the fifth term. Hey, look at that. To get the nth term, I'm multiplying by n, the number of the term. Okay. So what I'm going to do here is, as I write this rule, to come up with the nth term, I'm going to take 1 over the number of the term times whatever came right before it, which in this case is going to be a sub n minus 1, meaning the previous term. Okay. Now again, because it's a recursive rule, I have to identify, hey, what's the first term? So hey, the first term is going to be 1. So if I want to get the second term, I'm going to take the first term, 1, times 1 over the number of the term, 2. So 1/2 times 1 is 1/2. And then to get the third term, I'm going to multiply the previous term by 1/3, and the fourth term by 1/4, and the fifth term multiply by 1/5, etc. So there would be my recursive rule for that kind of funky sequence. Again, a couple of units from now we'll learn what this pattern is, the 1, 2, 6, 24, but not now, so you just have to wait. All right. Another example here using a recursive sequence in a real-life type setting. Oh, I hate mosquitoes so much. So much. Anyways, in this problem, a mosquito population in a controlled laboratory condition is estimated to be about 500. Okay, that's what we start with. Each day, an additional 100 mosquitoes are hatched. Gross. Can't stand you mosquitoes. The population also declines by 85% every day. Oh, good. From a pesticide and other natural causes. Good. Write a recursive rule for the number a sub n of mosquitoes at the start of the nth day. Okay, and then we'll talk about this find the number in just a minute. So, things that I know. I start with 500 mosquitoes, and then each day I'm going to lose 85%. Okay, if I lose 85%, well, I write that in terms of a math equation. I like to think about what I keep. Okay, so if I lose 85%, I'm keeping 15%. Okay? That's keeping 15% of 500 is what we're going to have left after, we've killed a lot of mosquitoes. The problem is then we're also going to add 100 mosquitoes after that. So after we kill a bunch of them, well, the ones that are left have babies, and now there's all of a sudden 100 more mosquitoes that have been hatched. Okay? So if I wanted to find how many mosquitoes there were the next day, that's what I'd be doing. I'd be taking 500 times 0.15 plus 100. So checking that out real quick, 500 times 0.15. And again, that's 15% of the number we started with. Okay, and then I'm going to add 100 to it. So I hit enter. I get 175. So that's the number of mosquitoes I'd have on day 2. Now, understand this is not a rule. This is just us putting numbers in order in an equation. We have to write a rule for a sub n. Okay, so I just wanted to write that out so you'd see what this might look like. To find the nth number of mosquitoes, however many mosquitoes are on day n, I take the previous number of mosquitoes, whatever it is, the day before, and I multiply that by 0.15. So that's the, I lose 85%, so I keep 15% of the mosquitoes that there were, and then I add 100 to that number. Okay, so there'd be my rule. Again, recursive rule, got to say where we started. So provided that the first term in this case is 500, because that's how many mosquitoes we start with. Okay, there's my rule. That'd be it. Now, I want the number of mosquitoes after the 5th day it asks for. Okay, here's a neat little calculator trick. Okay, with recursive rules and the idea of iteration, which we'll get into next, I can use my calculator to do a lot of that work for me. So 175 was the previous answer. Okay, and actually I'm gonna start over. I'm gonna take 500 and hit enter, so that's my previous answer. To use this recursive rule and iterate it, which again, next video you'll hear that word, but we're gonna take that previous answer times 0.15. Okay, or the first term times 0.15, and then I'm gonna add 100 to it. The neat thing about your calculator is because I have this ANS, it's going to take the previous answer, whatever it is, and plug it into this formula. So when I hit enter, it takes 500, plugs it in, spits out 175. That's how many mosquitoes are on day 2. Now for day 3, just hit enter. Takes the previous entry, plugs in 175. Now there's this many mosquitoes. Okay, so that's day 1, day 2, day 3. You want day 4? Enter. You want day 5? Enter. Boom. So we'll round up this part of a mosquito. We'll round up and say there's 118 mosquitoes there on day 5. Okay, so we'll say a sub 5 equals 118. Okay, roughly. Make that an approximate symbol. Okay. Now, describe what happens to the mosquitoes over time. Well, in this particular situation, if we were to run this formula over and over and over again, which our calculator can do very well, if I hit enter. 117.67. All right, and again, and again, and again, and again, and again, and again. Eventually, I'm kind of getting to the same number. I'm right around this 117.647. At some point, it sort of levels off, and this is our consistent number of mosquitoes that we have on a given day. So I'd say over time, we're going to have about 117, 118 mosquitoes left according to these situations. So that's part 2 of recursive rules. There's going to be one more thing on iteration.